So what are we going to do now, the rest of the day? Well, the rest of the class, what I want to do is talk about some more issues that we haven't quite gotten to, and then wrap some things up in terms of reviewing what we've done, and also talk about some of the things that we haven't done, and then even fill in the details of some things that we haven't done. So the first item that I want to talk about has to do with fit statistics, okay? So when we talk about fit statistics, what are we talking about? Let's talk about that here. We'll talk about fit statistics. We're talking about something we mentioned and we spent some time on in Epi 740, where we talked about goodness of fit, and it had to do with when you go through a modeling strategy of some kind to come up with a best model to describe an answer to your the research question that involves some kind of mathematical model that you're using. Typically, you want to also know not only what the odds ratio or the risk ratio, whatever it is that describes the association, what the whether it's significant or not, to measure something about the precision. You also typically want to know whether the model that you've decided is your best model fits the data well. So that's what we mean by goodness of fit. And you may recall back in 740, so long ago, that there was this goodness of fit measure called the Hosmer-Limassow statistic, which was the main measure that's used when you're doing logistic regression. That's the measure that's used. Now there are measures of fit or goodness of fit that are output in the three programs that we're primarily using in this course, which is Mix, GenMod, and GlimMix. So I want to talk about that to some extent. But basically, if you remember, when we also talked about fit, we started out talking, before we even talked about the Hosmer-Limassow statistic, we talked about this measure called the Deviance. Remember that thing called the Deviance, which was a way that you could talk about, you can test whether a model fit the data well, and that was a chi-square test that involved your considering in some sense the likelihood function for the model that you fit compared to the likelihood function for a model that might be called a fully parameterized model that you might be able to get if you considered all the covariant patterns in your data set. There was this statistic called the Deviance statistic. Now, when one is doing Proc Mix, GenMod, and GlimMix, there are statistics that come out of these programs that are sort of like Deviance statistics, that depending upon their value, you can decide whether the model fits well or not. They're actually not test statistics. They're statistics that are numerical. In other words, you get a value, like you get a deviance value of a certain amount. You could say whether it's significant or not. For these deviance statistics, or these kind of deviance statistics, for these three models, you're really not going to do tests. What you typically do is, if you have a model that you've gotten from your research process of fitting your model and coming up with the best model, you have this statistic. Now, if you want to compare this goodness of fit statistic or this deviance type statistic, if you have several models that you want to compare, you wind up using the program that you're using, whether it's Mix, GenMod, or GlimMix, you wind up getting this same deviance, whichever, there's some different types, but you'll get whichever type you decide, you get that computed or output for every model that you want to compare. So if you want to, if the goal is, I've got 5 different models and I wanted to see which model fits better. That's sort of the use of this idea of fitting statistics when you're doing correlated data. And I want to see which model fits better. What you typically do is you run the program, you get this goodness of fit measure, which is one of several ones, and then what you do is you get that for each model that you want to compare, and you list them in a table, and the smaller the goodness of fit measure is, the better the model fits. That's the idea behind that. And so if it's a deviance type, if it's a log likelihood type of statistic, it's something similar to that. Then what you do is, if you want to compare 5 different models, you're going to get 5 different statistics, deviance type statistics. You're going to list them, and the one that's smallest is the one that you're going to say is the best fitting model based on this measure that's being used. That's the idea. Now the problem with this is, well, one problem is you have some choices. So let's look at that. So I say mixed gen mod glim mix procedures provide fit statistics to allow the user to assess the fit of model to one's data. Now typically one way this is going to be used, and we're going to talk about this some more throughout this class today, is this whole issue about how do you choose the correlation structure. You know, what's the right correlation structure? And typically the fit statistics issue here is usually focusing on what correlation structure you think is best based on these fit statistics. So you might have 5 different correlation structures: exchangeable, autoregressive, unstructured. You might have fit statistics for each one of these things. You list them, and the one that's the smallest value is the one that's sort of saying, this is the model, this is the correlation structure that seems to give you the best fit. That's the way it sort of works. Now, so what I'm saying is one way, what I say here, one way such fit statistics can be used is to compare several candidate models. That's what I'm saying. See which is fit better. A list of such fit statistics for different models of interest can be formed, listing the models from largest to smallest, and typically the lower the fit statistic, the better the fit. And this approach has often been used to help decide which that's what I've just been saying, okay? That's what I've written over here, okay? Now, there's a problem with that. The problem with that, well, let's first talk about what these programs do, okay? Okay, here's one of the problems that I said down at the bottom here. Note, however, that the use of such fit statistics to determine your best model has the flaw that it is using a data-driven procedure. It is possible that the model with the lowest value of a given fit statistic does not make any conceptual sense. Just because you get this fit statistic for a certain correlation structure that's the smallest doesn't mean that correlation structure makes any sense at all. I mean, it may be that you've got some kind of a study like the aspirin study, where it was a cross-sectional study, and it doesn't make sense to use autoregressive because that's a correlation structure that doesn't make sense because you're not doing a longitudinal study. And it may turn out that if you just put in your running of a program autoregressive, you might not make sense to do it. Maybe that's the one that gives you the lowest fit statistic. So if you get that, then it's not a good idea to say, oh, okay, AR1 is the best correlation structure, because it doesn't make sense. That's what I'm saying. So consequently, caution should be used when using only fit statistics to determine one's best model. So I'm going to talk more about that in the whole bigger picture of how do you choose the correlation structure. But what I'm saying here is that the use of these fit statistics does help you to go through this process to help you decide what model might fit better. But it's not the only thing. It's not the only thing you use. Okay, so let's go on here a little bit. Let's see. What do I say here? Also, fit statistics use different calculation formulas. So there's different fit statistics on whether the procedure is mixed, gen mod, or glim mix. And therefore, separate listings of fit statistics need to be used depending upon which SAS procedure is used. So let's look at this now. So if you're using proc mixed, so you're fitting a linear model, and you're using proc mixed to fit that. Now, remember, as we talked about, and Zach illustrated in his lab, that not all of you came, but he's got it on Blackboard. If you're doing proc mixed, you can also use glim mix to fit a linear model. But if you're using mixed and you fit a model, here's a a code for running a proc mix model, and this is the Give Me 5 data set. For some of you are doing that for your project. You will get in your output a listing of some fit statistics, and these are a bunch of different ones. One is -2 log likelihood. That's sort of like the Deviance statistic. And then there are 3 other ones, AIC, AICC, and BIC. These are all variations of values that are computed using this -2 log likelihood that supposedly have their formulas that involve this -2 log likelihood, but they're considered to be based on the people who worked on them and developed them, sort of a little bit more sophisticated ways of determining fit. Although you notice all these numbers aren't much different from one another. Notice that? And these are numbers you're getting from fitting one model. And you notice this is a model, if you look at the code here, this is a model that's, what's the R matrix for this model? What's the R matrix for this model? Independent, because you don't see a random, you don't see a repeated statement that gives you an R matrix, so that means the R matrix is independent, and it basically says it's a mixed model where there are 2 random intercepts. It's a multi-level model involving, and it's in this case it's a linear model because it doesn't have a link function that says it's different, so it's a linear model, and that's what I said over here. But what this basically says is it's giving you 4 values, each of which is a different, more or less similar type of measure of fit. And which one you decide to use doesn't usually matter, is what I'm saying, because they usually give you similar values. What do people use if you're using proc mixed? I don't think it matters, but most people might use AIC, but if it doesn't matter, who cares? That's what I'm saying. These are the 3 that's usually considered, and I'm saying if you want to use this, any one of them, pick one. Usually doesn't matter, and usually you get the same set of results if you're comparing different models, whether you use AIC or AICC or BIC to do it. These are just different variations on the thing. So these are the statistics that come out from mixed. Now, if you're using fitting statistics for mixed, but you're using GLIM mix with a linear model, then you get, not only do you get AIC, AICC, and BIC, you also get something called CAIC and HQIC and some other ones. But the last one here, HQIC, what do you think, and I think I've mentioned this before, what does the Q stand for? Quasi Likelihood, right? So that's typically the measure that you want to use if you're using a nonlinear model. But in this case, I'm still using a linear model. So if I'm using GLIM mix to do a linear model, I'm basically doing mixed because I'm doing the same thing. And GLIM mix and mixed will do the same thing. But I just wrote the code using GLIM mixed over here, and I wrote a random residual here. So I'm basically getting the same information as I got here, but I'm getting a few extra things because GLIM mix gives you a few extra fit statistics, but it doesn't usually matter which one you choose is what I'm saying. And usually it's among the ones that I've got sort of in bold over here. These other 2 and the -2 residual log likelihood are usually not used. So now what about, what else did I say? For GenMod, if you ask for the fit statistics, or it automatically gives you, what you get are 2 things called QIC and QICU. Okay, you notice in this case, this I've run this is the Give Me 5, this is the Give Me 5 data set, and I'm using Poisson regression, as you see, because I'm saying distribution is Poisson, and I'm running GenMod, and when I run GenMod, I'm getting different fit statistics. They got different names. And the reason why it's called QIC is Q is for Quasi Likelihood, and in GenMod, we're running a nonlinear model over here, so it's Quasi Likelihood is what you're using. You're not using a linear model. And you're dealing with correlated data for a nonlinear model. So these are the measures. But this is, if you wanted to run GenMod and you wanted to compare several models, you'd pick one of these, QIC for example, and you'd get a list of the QIC values for the different models, and the one that's smallest is the one that supposedly is the better fitting model, as long as it makes sense, okay, is what I'm saying. So that's, so in general, if you're fitting fit statistics for a GLIM mix, in general, when you're allowing yourself to not deal with a linear model, this was Poisson regression, this is Poisson regression for GenMod, when you're fitting a model that's a Poisson regression GLIM mix model, you're getting a whole bunch of fit statistics with slightly different names. Why are they called pseudo AIC and pseudo AICC? Where does the pseudo come in? You know the answer, right? What's the answer? Is that the way GLIM mix works with a nonlinear model, it does this transformation in order to make it takes a nonlinear model and converts it to a linear model, and then it runs proc mix. That's how it works. So the conversion of the original data to this linear model winds up to be giving you what are called pseudo statistics, or a pseudo or response vector, and so all these statistics are called pseudo fit statistics. But in any case, you're going to get a list, and you just have to pick one, and then use that to decide on what model you think of the models you want to compare is the best model. Again, regardless of which program you're using, and what you're going to do is you're going to pick the one that looks the best, and you're going to make sure that it makes sense. And if it doesn't make sense, you might pick one above it, the next highest, the next lowest, or the next low, or you keep going until you get something that's reasonable. But this is not the only way you're going to decide on the correlation structure. We already know at least one other way to do that. We talked about in the last two classes. Another way to help you decide on the correlation structure, or to be able to test hypotheses about correlation structure. What was that? That was the Cove Test method. Remember? The Cove Test option in GLIM mix was a way you could also make some assumptions or some assessments about correlation structure. So goodness of fit, using a goodness of fit, is not the only way to do that. There's a bunch of different things. In fact, we're going to go down a list of things just to make sure we have that in mind. And this is clearly one of the questions that people have about this whole process of how to analyze correlated data is, how do you go through, what do you do first, or what are some of the priorities of how do you take everything together? So we're gonna talk about that before I finish there. Let's see if there's anything else. No, that was it. That's all I wanted to say about fit statistics. Do you have any questions about fit statistics? Did I make myself clear about this? I mean, I'm just trying to say that you got a bunch of different ones. If you want to use fit statistics to make your decision, you list them in order, and, from largest to smallest, or the other way around for each of the models you want to compare. So that's fit statistics. Okay, so what are we going to do next? Well, the next thing I want to talk about is this: robust estimators. Now, what I'm going to say for a good part of this is something that's more conceptual than it is numerical. I want to talk about what a robust variance estimator is, sort of how it's computed. But we've talked about this in general anyhow. Do you remember, does anybody want to say something about what you think it means, what a robust estimate, why we use these things? Can anybody want to volunteer to tell us, the class, what's the idea behind a robust, why do we use robust variance estimates? And the way we use that when we're using like mixed is we use an empirical option. Remember, you put in an empirical option. What's the reason for doing that? Why do we use robust, and what are we trying to do? Okay, I was going to call you, Kevin. Okay, but you raised your hand, so I didn't have to call you. Other than the right. So what Kevin's saying is that it may be when you run a program and you choose a correlation structure, how do you know that's the right correlation structure? So what a robust variance estimator does is do what? What does it do?
Doesn't it allow the variance to be linear? So you don't have this, I guess it's a more conservative estimate.
Well, what it does is, in some sense, adjusts and actually what it does, it adjusts the standard error of your regression coefficient to reflect the fact that maybe you don't have the right correlation structure. It uses that to adjust the standard error. It doesn't really adjust the betas, the estimates, the beta hats. It just adjusts the standard errors of the beta hats. So by doing that, if you're taking a beta hat, dividing by its standard error, and squaring it to get a Wald statistic, which is what you do, you know, you might be getting a different Wald statistic if you use empirical versus if you don't use empirical, because you're changing the standard error. And supposedly, you're improving the standard error by allowing for it to reflect the fact that you may have chosen the wrong correlation structure. That's the idea in terms of that's what it is. So, so that's the main thing that you have to, you know, and of course, one question that has already been asked to me a couple of times, either in project group meetings or individual office hours, or even during the breaks, was, do you want to use the empirical measure or not? In other words, if you're doing correlated data analysis and you have this option, I want to use it. Now, if you don't use the empirical option, what are you essentially saying? You don't use the empirical option. What are you basically assuming? That the correlation structure that you're telling the computer that you're putting into the program, into your code, whatever it is, if it's AR1, is the right one. That's what you're saying, okay? And if you're using the empirical option, you're saying, well, let's adjust for it because maybe I chose the wrong one. That's the idea, okay? And when you don't use the empirical estimate, that basically says you're assuming that the correlation structure is correct. That's what you're saying. And we often call the choice between the empirical and the non-empirical. The non-empirical is often called the model-based. That's the terminology used. If you don't say empirical, you're essentially saying that whatever correlation structure you put in is the right one. You're using the model-based one. Okay. Now, in mixed and in GLIM mixed, you automatically get the model-based estimate unless you say empirical. That's what you have to do to get a adjusted or robust variance estimate. In GenMod, and I don't think I explicitly said that, in GenMod, you automatically get the empirical. That's what automatically comes out when you run a GenMod procedure. So if you want to tell the computer, if you want to be able to see what the model-based outcome would be, or the model-based standard error, you have to write something in there that says model-based. And you do this on the first line. You say proc GenMod, and you say something about the data set, and then you say model-based. You don't have to say, you don't say empirical, because empirical is already the default thing. So if you want to see the model-based in GenMod, you have to tell it that. If you want to see the empirical and using GenMod or GlimMix, you have to tell it. You have to tell GlimMix and Mixed to put the empirical, but you automatically get the model-based. So anyhow, so let's now look at this. Now, so again, when we talk about a robust test, just so I want to just get the idea of robustness. You remember when we talked about using a t-test or an estimator of variance in a regression analysis, said to be robust if the procedure performs reasonably well, even when the assumptions about the statistical model are not true. That's the idea when you say a measure or an estimate is robust, you're saying that it works even if my assumption's not true, okay? And what we're trying to do here is not exactly that, because we're not doing a test. What we're trying to do, well, eventually we're going to do a test. What we're trying to do is say, well, if the assumption I'm saying may not be true, how can I correct for the fact that it may not be true? That's what I'm doing. It's a little different. And the way I correct it gives me this corrected thing called the robust estimator. So, and when you're talking about correlated data, the robust variance estimate is also called, and I've introduced this before, it's also sometimes called the sandwich estimator or the empirical estimator. Okay? And the sandwich estimator is the thing you're going to see in any kind of literature that when you read something and it says, well, we use sandwich estimators, it's another word for robust. Okay? And what it is what I've already been saying is, it's a variance estimate take the square root of the variance, you get a standard error of a regression parameter that consistently estimates the true variance of the estimate, even if the assumption about the covariance structure of the regression model error term is incorrect. That's all I've been saying so far. So a robust variance estimator, or a sandwich estimator is another word for it, is just a corrected estimate. In other words, a robust variance estimate is, as I say, is a corrected estimate of variance that takes into account the true correlation structure, which you don't really know, because if you knew it, you would just use that. You know, what you're saying is, I'm guessing at it, and it's so the issue is, well, how does it ever know? If you knew the true, you'd just use the true. You'd say that that's the right one. So it's somehow correcting. How is it correcting? Well, in order to talk about that, we need to look at a couple of formulas to do that. But before, let's say a couple of other things. The sandwich, now there's this, one of the books that I mentioned that's a difficult book to read in terms of the detail, gets to be very mathematical, but by Fitzmaurice, Laird, and Ware, they have some things that deal with some of these issues without getting technical. And they say the sandwich estimator is a consistent estimate of beta, even if the working covariance structure W is not correct. So with large sample sizes, the sandwich estimator yields correct standard errors. And that's basically what I've been saying. That's what they say. Now, you might say, now here's a question here. Okay, if it turns out that no matter what correlation structure or covariance structure you specify, if you do the empirical option or you ask for the sandwich estimator, you correct for it. Why does it matter? Why don't you just choose independence as your correlation structure? That's what I'm sort of, formula for the sandwich test involves both the choice of W. Now, but I'm saying, why not simply use a working correlation of independence and use a sandwich estimator? In other words, why don't you simply just try, when you're running the model, just say, I'm assuming it's independence, an R matrix, I'm assuming it's independence, and then I'll correct for the fact that it's wrong, okay? Why don't you just do that? Why don't you not have to worry about other choices, okay? Well, the reason is, first reason is that the formula involves both the choice of W, both your choice of whether it's independent or autoregressive or whatever, and it also involves the true. It involves the combination of what you're putting into the model and what the true correlation is, what the true covariance structure is. So it may differ. The closer W, what it says, the closer W approximates the V, the greater the precision, but there's no guarantee for any W, if you take the robust estimator, you're going to get exactly the same answer. In other words, the adjusted standard error that you get for different choices of W won't necessarily be the same. They're correct for their choice of W, but they're not necessarily the same answer. So that's what I'm sort of saying. So it's a large sample property, but the basic thing is that you might get different answers depending upon what W you choose. W stands for the one that you specify, even if even for whatever the true correlation structure is. So that's basically why I'm saying. Now, I'm not sure if I got this across here. In other words, the question is, why don't you just use independence and not worry about the other ones? And I'm saying if you do, you may get an answer to whether your exposure variable is significant or not, but you might not get the same answer if you chose AR1 or unstructured. And that's because what you're doing when you're running a sandwich estimator is you're combining both the choice of the working correlation structure and the true thing, and you can get different answers. So that's basically the important things that are on this slide. The rest of it is not that crucial, so I'm going to skip that. Now, here's the formula for the sandwich estimator. Now, this is you look at this thing and you want to, you either get sick, you want to leave or something. Let me explain some things about this formula as to where it comes from. Okay, first of all, this formula is the product of three matrices. The R stands for a variance covariance matrix. And it's a variance covariance matrix of a set of estimates of your regression coefficients. And it's written mathematically as the product of three matrices. And you notice that if you look at these three matrices, the one on the left and the one on the right are exactly the same. M0, something called M0 inverse. If you remember the matrix notation, M0 with a minus one means an inverse, okay? So what you're doing is you're taking the inverse of some matrix called M0, multiplying it by a different matrix, M1, and then multiplying it again by the inverse, the same variable, the same matrix that you started off. Now, the reason why this is called the sandwich estimator is because this side and this side are the same. The two sides, the left side and the right side of this three-way product are exactly the same. So this is sort of like if you talk about a sandwich, M0 inverse is like the bread and the meat is M1, or whatever's in the middle of the sandwich. You know, the part of the sandwich that you're, other than the bread, is determined, is identified as M1. So that's why it's called a sandwich estimator, okay? Now, if you look at the formulas for M0 and M1, I've written them down over here. This is the formula for M0, and this is the formula for M1, which you actually have to, in order to get the sandwich estimate, you have to take the inverse of M0. Now, just look at this for a second without, again, getting all upset, if you can, or upset with me because I'm showing it to you, okay? So now, notice that M0, you see this W formula in here? What does W stand for? What does W stand for? I've used it on previous slides. W stands for the working correlation structure. W stands for when you're running a model, it's what you're saying you think the correlation structure is when you're putting it in the code. I think it's AR1. That's what I'm working with. So you notice that this formula, M sub 0, involves an expression where in that expression is the working correlation structure. That's part of the process. That's part of the way it's computed. And the rest of this part of the formula, well, there's a summation side. The rest of this formula has to do with taking derivatives of the model with respect to each parameter. So what I'm trying to say is M sub 0 involves, the only thing that it involves as far as a correlation matrix is the working correlation matrix. Now look at M1, which is the matrix in the middle. Look at M1, okay? In fact, I'm going to put M1 up on the next slide. Here's M1 again. This is the formula. Here's M1, and this is what M1 is. This is, I'm just writing it again on this next slide. Now you notice this formula for M1 involves not only the W, the working correlation structure, it involves this expression, this term. That's what's in M1, okay? That's how M1 differs from M0, okay? Now, it's this part of the expression that makes this whole sandwich estimator something that reflects the true correlation structure. Now, how to, you know, without knowing what it is, okay? Now think about this. This, just look at this part. And now I've written it a little bit bigger over here. Yi minus mu sub I. What's Yi? Yi stands for the responses on the ith subject. What's mu sub I? Mu sub I is the expected value of the response, what you would expect the y's to be. So if you get the response and you subtract from it what you expect it to be, what's left? The error. What's left over of predicting y from what you expected from your model. So yi minus mu sub I is an error term. Is an error term for the ith observation, as is this, the other side of this thing. There it is again. Okay, but what's the difference between what's written over here and what's written over here? This, you notice there's a prime over here? You remember matrix mathematics when you had a matrix and you put a prime, what did that mean? That was the transpose of a matrix. So if the matrix was a column vector and you put a prime next to it, that would make it a row vector. I don't know if you remember that. Okay, so this is a column vector multiplied by, not a column vector, but a row vector. The dimensions, if you've got a subject who's had, let's say the ith subject has 4 responses. This vector would be a 4 by 1 vector. This vector, yi minus mu sub I, would be 4 by 1. It would have 4 rows and 1 column. It would be a column vector. What would this one be? yi minus mu I prime. If you've got a person with 4 observations, if yi minus mu sub I is a 4 by 1 column vector, what's yi minus mu sub I prime? Is it a 4 by 1 vector, or what is it? It's a 1 by 4 vector. So what you're doing is you're multiplying a 4 by 1 vector by a 1 by 4 vector. And that's allowed in terms of matrix multiplication because 4 by 1, the 1 in the number of columns in the first part of the product has to be the same as the number of rows in the second part of the product, and they are 1. 4 by 1, 1 by 4. That allows you to do that. Okay? So what are you getting if you multiply a 4 by 1 by a 1 by 4? What's the dimensions of that matrix? 4 by 1 by 1 by 4. It's going to be 4 by 4. That's what you're going to get. It's going to be 4 by 4. So what you're actually getting here is an estimate of a 4 by 4. It's really a correlation estimate or a covariance estimate because you're dealing with error. In fact, here it is. Here's the formula. Here's sort of a way of breaking it down. Y minus mu is equal to E. Y minus mu hat is E hat. Y minus mu times Y minus mu hat prime is E hat times E hat prime. And what you're doing is you're multiplying this column vector by this row vector. And when you do that, this is Ni by 1, this is 1 by Ni. You're getting an Ni by Ni vector. And what you're basically doing is you're having a bunch of terms in here which represent variances and covariances. And so this expression within this formula for M sub 1 is giving you an estimate of a covariance matrix. But you notice it doesn't involve, this calculation doesn't involve W sub I. Doesn't involve the working correlation structure. It's a way of getting an estimate of variance and covariance without putting in the working correlation structure in there, without putting in that in the formula. Okay? And so what you wind up getting is you get this M1 part involves the working correlation structure and some estimate of the correlation structure that doesn't consider the working correlation structure, which you might say is an estimate of the true correlation structure. That's why the M1 part in this formula is allowing yourself to correct for the fact that maybe you can put something in here that allows you to consider what the true correlation structure is. That's all I'm saying, okay? And so what I'm saying here is that when you use this formula for M0 minus M0 inverse times M1 times M, you're actually using a formula that involves a part that involves the working correlation matrix and a part that involves some estimate of the covariance structure that doesn't consider the working correlation matrix. And so it involves both of them. So that's why it's called a sandwich. I mean, it's not why it's called a sandwich. It's a sandwich simply because the left side and the right side are the same thing. But it's called an estimate that allows for taking into account the fact that you may chose the wrong correlation structure because it's putting into this estimate something that doesn't assume you know that you're using the working correlation structure. That's why it works. Okay. Now, what all of this come down to is if you were just using the non-robust or the model-based estimator, it would just be M0 inverse. But because M0 inverse times itself times N is just itself. So that's what the non-robust estimator. But the robust estimator allows you to consider, in addition to the working correlation structure, something that measures the true correlation structure. Now let me show you this. This is the last thing I want to do about this whole thing a little bit. Look at this slide here. There's two parts of the slide. Okay, see if you can follow this. On the row part, I have the robust variance, and then I say the true covariance structure. That's the columns. So I'm saying, suppose the true covariance structure was AR1. Okay. The row says, suppose it turned out that the working correlation structure, the one that you actually chose to run in your model, was not AR1. Suppose it was exchangeable. Suppose you chose, when you ran your data, an exchangeable working correlation structure, but the true working correlation structure was AR1. you see this check that corresponds to E and AR1? There's a check here. What's the check mean? That's what I'm saying. The check means it's a valid test. Why is it a valid test? Because what you're doing is you're using this working correlation structure, but you're using a robust variance estimator that's correcting for what the true correlation structure is. So any part of this matrix here, any check mark here, the reason why they're all checked is because they're all correct, valid estimates. But you notice the one on the right. Look at the table on the right. So suppose I use a non-robust variance estimator, and the true estimator, again, suppose the true estimator is AR1, and I use the true correlation structure is AR1, and my working correlation structure is exchangeable. Why do I have an X over here? Why do I have an X here and a check here? Why is the X over here? That's what I'm trying to get you to. It's really the same. I'm saying the same thing. Why is there an X? Or let's put it this way. Why is the X over here? Is there an X over here, a check over here, and why is there a check here and a check here? Why is there a check here? Because what you're doing here is you're choosing a working correlation structure to be exchangeable, and it turns out that if it turns out that the true correlation structure is exchangeable, then you're doing the right. You're making a valid estimate. You've actually not adjust. You're using a non-robust variance, so you're not adjusting for anything. So the only time you really can justify non-adjusting for anything is when the working correlation structure is actually equivalent to the true correlation structure. That's why there are check marks only on the columns here, on the diagonal, and these are all X's. The reason why there are X's here is because you've got a working correlation structure that's different from the true correlation structure, and you're using a non-robust variance estimate. So you're not doing a proper test. You're not, you don't have a valid test when the X's denote non-valid tests. So what it all comes down to is what we said at the beginning. This is all maybe more than I need to have done here. The message here is, if you want to use a robust variance estimator, it's because you're worried about correcting for the fact that maybe you chose the wrong correlation structure. And the only time you shouldn't be worried about that is if you really think you got the right correlation structure. In other words, if you chose exchangeable and the true correlation structure is exchangeable, then you're okay. That's what this says. But if you chose exchangeable and the true correlation structure is something other than exchangeable, you're not okay here, but you're okay here as long as you're using a robust variance estimate. That's what this says. Okay. Now, I don't know if this leaves you cold. Probably does. Makes me feel cold. I don't know. No. Okay, so let's skip this. Okay, now let's talk about this. This is the last thing I want to do before, well, I'm not going to be ready to take a break before I get on to the next topic, which is a summary of all this. Okay. So let's talk about this. What am I saying here? What is this slide about? The title is Options for Determining the Correlation Structure. So what am I doing on this slide? What am I doing? What I'm doing is I'm saying this is a big problem. This is the main reason why we're doing this course. Main reason why we're doing this course is we've got correlated data. In order to deal with correlated data, we have to do some kind of analysis. We have to somehow put into the analysis some way of picking out what we think the correlation structure, some way of putting that into the analysis. How do we do that? What are some of our options for doing that? Okay, and this thing lists the options. It lists just about every option I can think of. Okay, now if you look at this list and you say, okay, what does this actually tell me about the answer to the question? How do I choose the correlation structure? What this tells you the answer is, it depends. That's the answer. It depends on any one of these options and how you put them all together and make some sense out of what you get from these options. That's what this says. In other words, here's a list of things to consider. Depending upon how you answer these questions, any one or more of these questions, you might make a choice about what you think your correlation structure is. But we'll look at the first choice. Use what makes sense clinically or biologically. That's the first choice, right? First choice is you've got correlated data, and let's say it's like the aspirin bypass study, the aspirin bypass study. You know, if you remember, that study was not a longitudinal study. You were following people. 1 year later, people had bypasses. You're looking at the information on whether bypass is blocked or not, and it's cross-sectional information at 1 year later, okay? So it doesn't make sense to use AR1 as a measure of the correlation between the blockage scores, blockage 0 or 1 scores on each of the bypasses on a given person. So what makes sense clinically or biologically if you're using the aspirin bypass data is exchangeable. Like, makes a lot more sense than AR1 and makes a lot more sense than even stationary, which allows you the thing to be different for different, so you may decide that this is what you want to do. So in other words, the first thing on this list basically is one way to go about the process. Just say, look, I'm going with this. I'm just going to go with this, and I'm going to use this. As far as I'm concerned, this is the right correlation structure. I'm not even going to use an empirical estimate for it because it makes most sense that this is it. Now, you might say that makes sense. Well, maybe it makes sense for the bypass study, but if we're talking about another study where it is longitudinal, then we may have some choices, okay? So if we choose, and it could even be exchangeable, it could be AR1, it could be stationary, it could be unstructured. There are a lot of different choices, okay? So if we use what makes sense clinically, biologically, and we just stick with that, and we don't use empirical, then we're taking a chance. So that's why we might want to use empirical. That's what one of the things down here, compare empirical with model-based. That's one of the other things to add to this list. Start off with what makes sense clinically or biologically, but depending upon the kind of study you're doing, you might say, well, I'm not so sure about what makes sense. I'm going to check and adjust for the fact that I may have made the wrong thing. Well, that's the second one. But you notice it's not the second. I didn't have it underneath that because there are others, okay? Look at the second one. That's the second one that I've talked about, but the second one on this list is try several different correlation structures, okay? So another approach to this thing is, well, okay, there's something that makes sense, but there might be several other choices, okay? So what I'll do is I'll run a model with one choice, and I'll run a model again with a different choice, and I'll run a model again with a different. So that's how you can do your project. You can try 4 different choices that might make sense, and then you look at it might make sense, or some of them may not make sense, and you see what you get, and you do some other things with those choices to make a decision about which choice is better. So that's the second thing. Try different. Now, for example, suppose you try 5 different correlation choices. You run the model 5 times for the 5 different correlation structures, and no matter what choice you made, you get the same conclusion about the effect of exposure. So are you going to like that? And the answer is yes, because it didn't matter what the correlation structure you chose. It's allowing for different ones, but you got the same conclusion about the exposure disease effect, the exposure health, the relationship between the exposure and the health outcome. So if you try several exposures and you get the same answer, well, fine. If you get different answers, you got a problem. Because then you have to try to figure out, well, you know, among the different answers, what makes most sense. So you got problems there, okay? Okay, so that's the second one, okay? There are others on this list. Another one is use unstructured. If you don't know what it is, if you don't have a clue, why don't you start with unstructured? That's another thing. That's another goal. You know, I don't have a clue what it is. It may make sense to be exchangeable AR1. Why don't I start with the most complicated one and then work with that, okay? Or see what I get. Run unstructured. Let the computer estimate what the unstructured, correlation matrix is, and then see what I get. And does it look unstructured? Does it look exchangeable? And maybe change your mind after that. Okay, so that's a third one. So there are all these things. None of them is exactly right. They're all different options. Okay, so I'm just listing it through it. Another one is this is what I was sort of getting at, is start with unstructured and then simplify. And all I mean by that is, again, what I was saying is you try to run unstructured. You tell the computer the covariance structure is unstructured, and then you look at the output, and it'll give you an estimate of that unstructured correlation matrix. And the estimate will be all those correlations will be different. But maybe they're not all different, and maybe they all look the same. If they all look the same, then you might say, hey, I could maybe argue that it should be exchangeable, even though I allowed for it not to be exchangeable. So that's another choice. Start with unstructured and simplify. Okay? And there are others. Okay, let's look at some of the others. Start with toplets or stationary and simplify. Remember I talked about stationary. Start with toplets or stationary and simplify. Now, one reason for starting with toplets or stationary is you think that might make sense. There's another reason for starting with toplets or stationary, if it's longitudinal, is that what frequently happens, particularly with unbalanced data, is that when you try to deal with correlation, particularly for unbalanced data, you try to run an unstructured thing, it doesn't run. You get non-convergence, you get some error message that said you can't get an inverse of a matrix or something like that, and the unstructured doesn't work. So an alternative to unstructured is toplets or stationary. Okay. Now, you remember when I gave you that? Now I'm gonna jump to some. Oh well, can I jump to it? Let's see. I'm gonna jump to this. I'm watching the clock here. I'm gonna jump to this by showing you something. Okay. Let's see. I'm skipping to something, but this is in the next set of slides. Nope, not there yet. Okay, look at this slide. Okay, look at this matrix. This is the next, I'm going to get back to that, this slideshow, but look at this matrix over here. Now, you notice what I've written on this matrix. Is this matrix unstructured? Is it unstructured? Yes or no? It's a correlation matrix, right? Because I have ones on the diagonal and I have rows on the off diagonal. Is it unstructured? Are all the correlations different? Are they all different? How many say they're all different? How many say they're all the same? How many say some of them are the same and some of them aren't the same? Very good. Okay. Good. We're together on this thing. So what are the same? You notice it says row 1, row 1, row 1, row 1. This is a 5 by 5 matrix. What does that mean? Row 1 is the correlation between the first and the second. What's this? That's this one. What's this one? Between the second and the third, right? This is the third and the fourth, and this is the fourth and the fifth. So these 4 row 1s, it's the same number, but what you're saying is any correlation that's between adjacent observations that are only 1 unit apart are the same. Okay? Okay. What does the row 2 say? What does that say? Any pair of observations that are 2 units apart, 1 versus 3, that's this one. 2 versus 4, 3 versus 5 are the same. Okay? That's what this one says. Well, this one says any pair of observations that are 3 units apart are the same. Not 2 units, or 3 units apart. And there's only 1 left over. You know, this is an example of a stationary. What would you say? It's called the stationary. It's called the stationary forward dependent because there are 4 different values that you get for the correlation matrix. It's called stationary forward dependent. This is one of them. This is the second one. This is the third one. There's 4 different values for the correlation. That's why it's called stationary forward dependent. Okay. Now, is this matrix unstructured? And the answer is no. But if you tried to do unstructured, if you ran a model where you said, let's try unstructured, and it didn't work, you might say, maybe this is an alternative to that. Another alternative that looks like it's got several correlations in there, even though it's not unstructured, at least it's got a bunch of different ones in there. It's not, so this might be the second alternative you have. Okay? This is called, again, stationary. In this case would be stationary forward dependent. Now, the thing about this slide is GlimMix and GenMod have different terms for stationary. That's what I have on this slide. GlimMix and Mixed call that a stationary correlation structure. It calls it toplets. And GenMod calls it stationary. Okay? And in fact, a stationary forward dependent, this is stationary forward dependent because there's 4 different correlations in here, is equivalent to a Toeplitz 5 dependent. That's just the way it works. That's just the way. So if you're running mixed or glim mix, you just got to be a little careful to say if you're doing Toeplitz 5 dependent, that's equivalent to a stationary 4 dependent. But that's not my main point here. Was just to get back to this other slide. The other thing was to basically say that this is a reason why you might want to start with Toeplitz or stationary. It might be that you try to do unstructured and it doesn't work, and you want to do something that's not it's not unstructured, but it's something that allows you to get a lot of different correlations, even though some of them are the same. So that's another choice. Okay, another choice for the correlation structure, which sort of could ignore all these other choices if you want to, is just use the goodness of fit statistics. Just use that to decide on the correlation structure. Fit a bunch of different models. Look at the whichever AIC or BIC or QIC statistic you want to, list them and make your decision. Well, we know that's flawed by the fact that the lowest one might not make any sense. It might be something you want to do in conjunction with the other ones. So there's a list of things here. That's all I'm saying. Another one is use the estimated correlation matrix from the Ys, from the actual data themselves. In other words, you got a bunch of responses on each person. You got 100 people. You got 6 responses on each of 100 people. Form that correlation matrix and use that as the input. Okay, whatever it is, it's probably going to be unstructured, but use that correlation matrix as a fixed correlation matrix. In other words, use those numbers to put them in there. Well, the problem with this is that what you're doing is the model does not just involve Y, it involves some parameters in the model that represent getting the expected value of Y. And you've got to sort of remove those parameters from the response in order to, you're really interested in the error term, not Y. You're interested in what's left over after you consider what the expected value of Y is. So this wouldn't be right, even though that's a choice some people make. So I'm just going down the list. Another choice is start with independent, fit the model, obtain residual, then use correlated matrix of residual. This is actually what unstructured is. That's how unstructured works. That's how the computer does unstructured. So this is no different and might not work if unstructured doesn't work, because it's the same thing. Another choice is, I didn't even get into this, is at some point, if you're choosing what's the right correlation structure, well, maybe you have to decide, I didn't even mention anything up to this point. Should you use fixed effects and random effects? Should you have random effects? What random effects should you have in the model? So you might also consider random effects to help you decide what the correlation structure is. Now, it's getting to be a mess, and that's why it's and I already said compare empirical versus model-based, and the last thing on this list is use the Cove Test statement and Glimmix to help you test some hypotheses about the correlation structure. So all this says is that if you want to come up with the right correlation structure for your project, or for any project that you have after you finish here and you go out in the world and you have correlated data, there's a whole bunch of things to consider. And you have to sort of go down this list and make some decisions depending upon what you have, what you decide to do. And that's what you need to do for the project. Not necessarily all of these, but you need to sort of consider this list. That's why I have the list there. Okay? And there's no easy answer. There's never an easy answer to most of this. Okay? So follow me in terms of that? I hope you do. Okay, now it's 3:45. Okay, so what I'm going to do now is get out of this. This is the last slide over there. So what I'm going to do now is I'm down to the last thing I wanted to do. The last part of the class today has to do with, it's going to take a little while to talk about. It has to do with a summary of what we've done in this course and what we haven't done in this course. What we haven't done and what we've done. And in the what we haven't done, I've got some extra things to say. So it is 3:45. Let's take a 15-minute break. So this is an early break time. Is that all right? An early break time? Or do you want me to keep going? Let's take an early break. 1:45. Let's come back so we'll finish early. Let's come back at 5 of. Let's take a 10, looks like a 12-minute break. So let's start at 5 of. And then I'm going to start talking about what's in this slideshow. That's the last thing we're going to be talking about, but there's a bunch of stuff in here to talk about, okay? So we got sort of 10 minutes, all right? I'll be around here to ask any questions, and you guys are not moving, so I'm not sure what that means. Does that mean you're just stone cold? This stuff makes you cold, makes you freeze, turns you into stone. Maybe it does, you know. It's not that easy, but, okay, so that's what we're going to do after this break. We're going to start talking about this. I'm going to do this. Okay, let's start again. So, first thing I want to do now is to just go over what I think you more or less already know, that between the start of the semester and now, you've already more or less learned, even though in this list I have some question marks because there are issues that aren't fully that easy. But the first thing is the notation for what you need to do in order to talk about correlated data. We've spent some time talking about notation. And one of the key ways to describe the model is the notation for the ith cluster. In other words, a cluster-specific notation, y sub I, the set of observations on the ith cluster, on the ith subject. And we also talked about notation for, notation matrices and how you deal with matrices to some extent. And for the most part, this is not something, matrix mathematics is not something you really have to worry about, but the more you understand what a matrix is and how it works, the more you can follow some of the literature and even some of the slides that get a little bit more complicated, like what I did when I talked about the robust, the sandwich estimator. We've talked about the data layout, what the data layout looks like, and we've talked about that the data layout is sometimes comes in your data horizontally, but the way you really want to set it up is vertically. In other words, you want to have for each cluster or each subject, if the subject is the cluster, you want to have the different repeated measures or observations within a given cluster lined underneath in a row underneath one another, and then the next cluster follows that, and that's what we mean by a vertical way of a vertical data layout. And then we talked about a number of things about the different approaches, but when we described the models, the different kinds of models, and this is true even though we focused originally on linear models, there were really three kinds of models to be concerned. One was called marginal models, and that was when there were no random effects, or there was no predictive variable that was an earlier value of y, and another was called conditional or transitional models, and a third one are called random effects models. And random effects models have, in addition to fixed effects, they have random effects in there. And one of the issues there was, which is really the next issue, is when to use random effects and what random effects you want to consider. But another issue, which I never felt, and I still haven't felt comfortable with, and we only spent a short time on that. Nobody's, I think, is doing any proposal, any project on this with this kind of situation, is how do you actually, what do you mean by a conditional transitional model, and how do you actually do it? How do you actually fit the model and draw conclusions? There are a number of different ways of doing it. So there are three types of models. And what we've primarily learned about in this course is how to deal with marginal models and random effects models, but I think this is still an up in the air issue that most of you, and I know myself, don't really feel comfortable with. When to use random effects? I mean, there's random effects in your model, but when do you use it? When do you decide to use random effects or not? And, whoops, somebody's helping with my conversation here. I mean, the one reason there were really three ways to talk about when to use random effects. And one way was when we had the FEV study and we were trying to say something about individual subjects. We have a cluster, the subject was a cluster. We had repeated measures on it. If we want to say something about what's going on with an individual subject, that's one reason for using a random effect, to be able to say something about individuals within a cluster. Another reason was in order to be able to get a correlation structure. For example, when you had the shoulder flexion data set or the gaze angle data set, and you wanted to be able to consider the fact that subjects were another factor, and you might want to consider a more complicated correlation structure than simply exchangeable or autoregressive. You might want to allow for there to be interactions of subjects, not only with a main intercept effect, but also an interaction of subjects with any of the variables that were in your model, and that's that's another reason for using random effects, when you want to consider a more complicated correlation structure. And the third way, which also involves a more correlation structure, when it turns out that one of the factors that you're really interested in, one of the exposure variables, like radar in the gaze angle data set, was a factor that you wanted to consider, and you really didn't consider that factor as a fixed factor. You wanted to consider that. Well, in that case, you have to put that factor in the model as a random effect. We talked about, after we dealt with the linear model, we then eventually started talking about how to generalize the linear model so that we can deal with the nonlinear model. And the two ways we generalize it is to talk about a generalized linear model, which basically is a model that has a linear component, and the way you specify the linear component is through something called the link function. So the link function could be logit, log, or just linear, or just identity, depending upon what the linear part of the model, what you wanted it to be. And then quasi likelihood has this way of extending your analysis to allow you to consider a situation where you actually don't know the likelihood, or you have a situation where the data is too complicated, either because the outcome variable is more complicated to figure out, or to figure out what the likelihood is, or you have correlated data, so it's not easy to come up with a likelihood function. And so that's where quasi likelihood comes in. It's an extension of maximum likelihood that. And when you extend to quasi likelihood, then one of the problems is you can't do likelihood ratio tests, because you don't have a likelihood function, but you can do score tests and you can do wall tests. So that's just reviewing that. We talked about the procedures that we talked about was mixed, GenMod, and GlimMix. Those are the three procedures. Now there are some others that I haven't spent time on because most people don't use them. One of them is something called NL mixed, and I've got a PowerPoint presentation in there about NL mixed, but it's really not very well used, so I decided I wasn't going to spend any time in class talking about it. You can read about it. Another thing about GenMod is that was different from what I talked about when I talked about GlimMix. Well, GenMod and GlimMix are different because GenMod doesn't allow random effects, right? That's one big difference between GenMod and GlimMix. Another difference is that GenMod allows you to consider a odds ratio structure rather than a correlation structure, which in some ways makes sense if you're talking about a binary logistic regression model. It's not easy to make sense if you have a ordinal or a polynomous logistic regression model or any other kind of model like a Poisson regression model. But the log OR is something that makes sense, and so we talked about that. I don't think hardly any proposal had suggested they were going to do that, but maybe one or two are, depending upon where they're at and what they think they can get done in the time frame that you're dealing with. Now, so GlimMix differs from GenMod in a number of ways. And one, GlimMix allows you to have random effects in there. Another thing is GlimMix is different because in addition to, and it doesn't deal with a log OR, doesn't let you get an odds ratio structure. Another way that GlimMix is different from either GenMod or mixed is there's no repeated statement in GlimMix, so if you want to consider an R matrix, you have to use a random residual. I'm just trying to review the stuff, and I hope you remember this, or this rings a bell here. So that's, in some sense, what GlimMix has to do. But the other thing about GlimMix that's different from GenMod is GlimMix actually solves the quasi likelihood problem differently than GenMod does. It uses a different way to do it, and the way it does it, it uses some kind of approximation. It's what's called the Taylor series approximation. And what it basically does is changes your nonlinear model to an approximate linear model and then uses mix to do it. And then as a result of that, when you're using GlimMix, what you're getting, the kind of tests you're getting, are F-tests and T-tests, which are the type of tests you get out of mixed. And when you're using GenMod, you get chi-square tests. And so there's a different kind of test. So one issue that we've talked about briefly is that if you have a GlimMix model that doesn't have any random effects, and you have a GenMod model that doesn't have any random effects, both of them, if the model you're dealing with is a marginal model, will they give you the same answer? And you might think that maybe they wouldn't if the approximation that GlimMix is using is, if it's using an approximation. But when you put in a linear model in GlimMix, GlimMix doesn't use that linear approximation. It basically just does mixed with that model. So GlimMix and mixed are really the same if you have a linear model. There's no difference between them. But there is a question about whether if you have a marginal model, will GlimMix and GenMod give you a marginal model that's like logistic, nonlinear? Will GlimMix, and if it's nonlinear like logistic, GlimMix is using this approximation with pseudo data, which is changing the observations to pseudo observations. And GenMod's not doing that. So you get the same answers. And most people, most of the statisticians that have written the program say more or less when you're dealing with a marginal model, you get the same answer. But I had a meeting with Toshihiro the other day. There he is, sitting there. And he said that he ran something, got different answers. He ran GenMod, isn't that correct? He ran GenMod and GlimMix for the same nonlinear, and it was it a logistic model or a Poisson model? I'm trying to remember. It was what? It was a logistic model. It's like the same situation. And one of the models, the GenMod model ran, but the GlimMix model didn't run. And the GenMod model ran with even AR1. The GlimMix model didn't run with either independence or AR1 or anything else. So it's not always the case that the GlimMix and this was a marginal model. It wasn't even a random effects model, and you didn't get the same answers. In one case, you didn't get an answer. So you may be faced with that. We talked about just before the break, we talked about correlation structures and how to choose, and the answer basically is it depends, and there's a long list of stuff. So I'm not going to go over that list anymore, other than what we've just said and some of the details about some of the specifics of it. One of the details is goodness of fit, and we just talked about that just about an hour or half an hour ago, different ways to do goodness of fit. That's something that you can do. It's not the only way to choose a model or to compare correlation structures. It's one of several things. We talked about empirical versus robust estimators, and most of the time, empirical / robust. It's not versus. It's just two ways of saying the same thing. Empirical / robust versus what? What's the alternative to empirical robust? It's called model-based. Okay. Where you're assuming that the correlation structure that was your working one is the right one. And most of the time, people don't feel that comfortable with their choice of their working correlation structure, so most people try to use empirical. And I think that's what most of you are going to do, even though there's no exact right answer. If it turns out that and I didn't say this before, but if you try empirical and you try model-based for the same data and you get almost exactly the same conclusion for a certain working correlation structure, that gives you some information that that working correlation structure is a good one. In other words, if you use model-based for, say, autoregressive, and then you use empirical for autoregressive, and the model-based gives you basically the same estimated coefficient, the same decision, then that helps to support the fact that the autoregressive one is probably a good correlation structure. You might not get that similarity with some other choice of a working correlation structure. So there is something to say here. And then we talked about multi-level and what that was all about, and how there are different ways to do multi-level. And just to rehash some of this, one way, the simplest way to do multi-level was to actually say, okay, multi-level involves predictive variables that are measured at different levels. For different, there could be at a individual level, could be at a higher level, a county or a district level or something like that. And the simplest way to write a multi-level model is just to put these different predictors that are measured at different levels in the model as predictors in the model, and then to decide, without doing anything more complicated than that, whether you want to have any random effects and which ones you want to put in the model. That's without doing anything more fancy thing that we talked about. But the other way to do that was to actually write the model at different levels, write the model at the individual level, and then at the next highest level, and the next highest level, and then combine the models to get a single model which might have whatever random effects make sense and whatever interaction terms make sense. And that's the way that most people do it. And you might get a very different kind of answer to what your model that you should consider is when you do it that way than when you just sort of decide to write the model from scratch without considering the different levels. So that's sort of what we did. That's what we've done. Is that right? Have we done this? I think we've done this. Do you feel like at this point that you have a clue on this stuff? I mean, I'm assuming you do, because, yeah. Daniel has a question? No. Just stretching. Okay. So, again, you know, my hope is that when you actually do your presentation and turn in your project, where everything's going to really come together. You're going to have to really wrestle with a lot of this stuff that maybe are unclear up to this point, but I think there's been a certain amount of clarity that keeps coming in from one week to the next. Okay, so what haven't we done? Okay, so let's look at this list. What haven't we done? Well, one question is when to use random effects. Now, I've listed, you know, some things. I mean, one way to decide to use random effects is that you want to say something about an individual subject, okay? Or you want to say have a more complicated correlation structure. But it's not only when to use, I should have also had when and how to use random effects. So another issue for whatever project you're dealing with is, well, if you want to consider random effects, what random effects do you use? Should it be a random intercept? Should it be a random slope and intercept? Should it be more complicated slopes for other? I mean, you could have an intercept term in the model, you can have an exposure variable, and you can have a product term involving an exposure variable. So you can have a random slope for a product term because it still involves the exposure variable. So how do you decide that? Well, it's not that clear-cut, but one way you could decide that is consider maybe the most complicated set of random effects you want to allow yourself to worry about, fit that model, and then try to simplify that model using some of the procedures we talked about, like Cove Test. It may be if you start with a random intercept, a random slope, and even another random slope for a product term, you might want to test something about some of those random effects in the model using 0G, or something which says maybe you don't need any random effects, or do something like that. So you can start with a model that's more that involves more random effects than you might think makes sense, and then get rid of some of them if you find that they're not significant. So that has to do with that. So we haven't fully answered that. I mean, there's still issues that you have to worry about. Choice of correlation structures. Well, I listed the choices, a whole bunch of choices, but it ain't easy. You know, you have to do it somehow. So that's why there's a question mark there, because you still have to worry about it for your own data, and everybody's data might be different in terms of how it's going to work out, and how you go through this list and all that is different for different folks. So now I want to say something about modeling strategy. This has come up. I'm going to say some more about this after I go down this list of what we haven't done. But you know, when we talked about when you had EPI 740, we talked about modeling strategy. We essentially had a couple of things. We talked about this model that was this hierarchical model that had an exposure, more than one exposure. It had some covariates in the model that were potential confounders, and had potential effect modifiers in the model, and you had to decide what that model was. And then you had to assess before you assess interaction, what did you have to do? You had to assess collinearity, and then you assessed interaction, and then depending upon that, you assessed confounding and precision. And that was sort of what you had to do, and that was the modeling strategy, essentially, that I described, or Eli and I described for EPI 740. But now when you're talking about correlated data, it's more complicated, because not only do you have to worry about what the initial model is and what the hierarchical backward elimination, you have to use that strategy, that BW stands for backward. You have to worry about, well, how do you deal with the fixed and the random effects in your model that you're going to consider using? How do you deal with the correlation structure? What order do you do it? Where do you consider the empirical option? When do you consider fit statistics? How do you use Cove Test? Where does multi-level come in? I mean, these are all extra things. The modeling strategy is much more complicated when you're dealing with correlated data. And most of you are going to have to deal with that. So I need to talk about that a little bit more. Details on conditional transitional models, well, that's an issue, but I'm going to leave that for some other year. I'm going to do that this year. There is an issue, what if the number of clusters is small? I haven't talked about that at all. I mean, the smallest situation is you only have one cluster. You only have one person or one cluster. For example, an example of that would be, I talked about, what was it, infection rates in a clinic a study that I worked with over at CDC, where you had a clinic and you were looking at infection rates from 1 month to the next over several months. Could be 80 months, and you had an infection rate at 1 month and another month and another month and so on, and you only had one clinic. So you had 80 rates, but you only had one clinic, so K is 1. So is that a problem? Okay. And it is a problem because, or there's something to worry about, because the reason why I have to worry about that is because the statistical assumptions that is typically made about whether you can do any of these tests, whether it's Cove Test, likelihood ratio, contrast, and all that, the assumption is that K is moderately large. Well, K equal to 1 is not moderately large. It's as small as you can get. And then another question is, what if K is not equal to 1, but K is equal to 10 or 20? So what do you do if K is not large enough for you to consider that you want to, you want to assume that it's large enough for you to assume that you can do all these tests? Well, there's a recent SAS input or SAS thing into the user's guide, which has to do with something called Mbn Adjustment. I'll show you that shortly. Okay, that allows you to deal with that, allows you to adjust for the fact that maybe you're worried about that you've got a small number of clusters. Okay, now how to decide that it's a small number or not? At least you could use the adjustment procedure and see if it makes a difference. In other words, you use the adjustment procedure and then you ignore it, and if you get very different answers, then you might say, I better use the adjustment procedure because that means that maybe my number of clusters are small. Okay. Another issue that's on this list that we haven't talked about is, well, we talked about Quasi Likelihood and GEE and GenMod and GlimMix, and we talked about how, with some examples of how you can use GenMod and GlimMix, where you've got a Poisson outcome, Poisson model, Poisson regression model, and you have a binary logistic regression model, but we haven't talked about or haven't illustrated anything about whether you could use correlated data and do a correlated data analysis when you actually have either a polynomous or an ordinal logistic regression model. And, well, it turns out that you can do that in GenMod and GlimMix, and I have a few slides just to talk about that, not to get into it in a big way, but some of you are doing that for your project. In fact, anybody here that is here doing that? I'm not sure. Maybe you're not even sure yet, you know. But it may be that some of you said, well, I don't know whether I can do this or not, so I'm going to use binary. But you might want to do polynomous or ordinal if it turns out that to use binary, you have a continuous outcome, and to be able to categorize it in two groups, you're saying, well, that's too broad a way of categorizing. I want to have at least 3 or 4 groups that make more sense. So you can do ordinal or polynomous logistic regression using GenMod and GlimMix. Now, one thing I haven't talked about at all, haven't put into the course, is recurrent event survival analysis. Okay. Now, there is in the, I'm not sure if it's either in the course documents or in the lecture notes, there is a PowerPoint presentation, a short one, that talks about how you can deal with repeated measures survival analysis. We haven't talked about that, and what I'm basically saying is, suppose you have a subject, and the subject's followed for a certain amount of time to see if they get a certain event. So time until event. Okay. Then they get the event, but they haven't died. You know, once they get if they died, they can't be in the study anymore. Let's say they get the event and it's a flu or it's a respiratory illness or something like that, and they have some downtime, and then they can get the event again. You know, and then they have some downtime and they can get the event. That's repeated measures survival analysis. Okay. And if you have data like that, you've got correlated data. You've got potential for correlated data because each subject can have more than one outcome, measure of an outcome. Okay? So how do you do that? Well, the slide presentation that I have in there is an example of a simple way to do it. And what it comes down to is what that slide, it says there's a way you can do it using pH-reg that allows you to get what's called the Sandwich Estimator. That's why I introduced that term, Sandwich Estimator. This program, the pH-reg, allows you to get sandwich estimators if you have repeated measures on survival data. Okay, so that's another thing. How to use multi-level programs, HLM, ML1, WinBugs, and how do they compare with GlimMix? Well, all I did when I talked last week about multi-level was to talk about multi-level in the context of using GlimMix with some examples. And I just very briefly said there were these other packages that do multi-level, and more or less they give you the same answers, more or less. But I had some slides that showed them, but I never really went into them. And for the most part, they compare. But you have one way to do it now. If you work part-time at CDC, they have these other packages, and some people at CDC use HLM, for example. They use that regularly. So if you're working there and somebody says, I want you to use HLM, or they're suggesting that, or you suggest that or something, you know, do you get the same answer as GlimMix? Well, supposedly you will, but you might want to run both just to see whether you are getting answers that are similar. Another issue which we haven't talked about, like what we haven't done, is what to do if there are a lot of zero outcomes. These are called extra zero and hurdle methods. So in other words, suppose you have Poisson data, counts. You got counts of the number of asthma attacks somebody has from one week to the next. And most of the time, somebody has no asthma. Somebody has asthma, but there are many weeks. You keep going from one week to the next, and there's several weeks where somebody has no asthma attacks. So most of the data has zeros in it, okay? And there's some of them when you have 1, 2, or 3 asthma attacks. Well, in that case, and this also could happen if it's a binomial situation, it could be mostly zero. In that case, there is some worry about the fact that the amount of zeros that you have is causing a problem in getting a bias. Somehow it's biasing the outcome because it's more tending towards zero, and you need to do something in the analysis to reflect that. And there are these methods called extra zero and hurdle methods, and you'll have to just look it up if you have that situation. We haven't had time to talk about it, but I'm just mentioning that. Another thing we haven't had time to talk about is how to determine sample size for correlated data studies. And on Blackboard in the I think it's the lecture notes, but it might be in the course documents. I do have a paper or two that references that issue, but we didn't have a chance to talk about it, and we're not going to talk about it. Okay, but that's an issue. If you're doing correlated data, how do you decide to do sample size? And I mean, one question is, if you have correlated data, do you think you need less data? I mean, do you need a smaller sample if you have correlated data than if you don't have correlated data? You could argue that maybe you need a smaller sample. I mean, in the extreme case, if you had correlated data, perfect correlation, you had repeated events, repeated outcomes for a given person, and no matter what repeated, they were exactly the same. The person got exactly the same outcome for all the repeats. Then you'd only need one measure on the person. You wouldn't need to do so you might say the sample size is smaller if the correlation matrix is really high. There's really strong correlation. That's what I'm sort of indicating. Now, whether that's true or not, I'm not completely sure. I don't think that's exactly true, but there are some papers about that. And if you're doing a study, either for your thesis, too late for that at this point, for your PhD dissertation at some point, this is something you may look at. So now I have some other slides that I want to talk about over the next, might be a half an hour, about some of these other things.